Ever thought about what it would take to have a truly interactive 3D map of a city? I mean, every single detail right there. Well, the tech behind that is often LiDAR light detection and ranging. Super powerful stuff. But getting useful information out of that massive amount of data, well, that brings its own challenges. Today, we're doing a deep dive into one specific solution: segmentation of LiDAR point cloud data in urban areas using adaptive neighborhood selection technique. Quite a mouthful.
It is, but the core idea is fascinating. We're looking at how researchers are basically changing the game for 3D city mapping, and they're doing it by fundamentally rethinking how we define neighbors within the data itself. You see, LiDAR gives you this huge cloud of points, millions, billions maybe. Each one has coordinates X, Y, Z, its exact spot in 3D space, sometimes color too. And that raw data is what we use to, pull out building shapes, map roads, check out the trees, all that.
Okay, so you have this massive point cloud, and the tricky part is figuring out which point belongs to what, right? Like this dot is a building wall, that one next to it is actually a leaf on a tree.
Exactly. It's tough in complex urban scenes. And researchers found something key. They realized the most critical factor for figuring out what a point is isn't just the point itself. It's the company it keeps. It's neighborhood.
Ah, the neighborhood idea. So what was wrong with how they used to define these neighborhoods?
Well, traditional methods often used a fixed size, like draw a fixed circle or a cylinder around your point of interest and grab everything inside.
Mm.
K-nearest neighbors is another common one. But cities aren't neat and tidy, are they? A fixed zone might grab points from a building roof, the tree next to it, maybe even some random noise point an outlier. And if you include those unrelated points when you're trying to calculate the geometric properties, you get significant errors. It messes up the feature extraction.
Right, like trying to describe an apple by including bits of the orange sitting next to it. Your description gets muddled.
Precisely. So these fixed approaches just weren't cutting it in these really diverse, heterogeneous urban environments.
Okay, so that leads us to the breakthrough. What was the adaptive solution they came up with? This sounds like the core innovation.
It really is. They did something quite clever. Instead of one size fits all, they first divide the entire point cloud into 4 different types of geometric regions.
4 types. How do they decide what goes where?
They use inherent geometric properties of the points and their immediate surroundings. First up is curvature. This helps separate, sort of, regular smooth surfaces, think building roofs, roads, from the more jumbled, scattered areas like edges, corners, or vegetation. Okay, then for those smooth, regular areas, they use verticality. Makes sense, right? It splits the flat, horizontal stuff like pavements from the upright things like building walls or poles.
Got it. Smooth gets split into flat and vertical. What about the complex, scattered bits?
For those, they use a property called omnivariance. It's a measure of how spread out the points are in all directions. Low omnivariance usually means sharp features like building edges or corners. High omnivariance suggests more dispersed things like tree leaves, maybe some rough ground, or even outliers.
Okay, wow. So you've got these 4 distinct zones: planar, vertical, low omnivariance edges, and high omnivariance scattered stuff. That's smart. And then they apply the neighborhood selection, tailored to each zone.
Exactly. That's the adaptive part. It's like using the right tool for the right job.
Oh.
For the smooth, planar, and vertical regions, they use an entropy-based method. It basically looks for the neighborhood arrangement with the least disorder, trying to keep things clean and consistent. For the low omnivariance regions, those sharp edges and corners, they use a normal direction-based method. This helps make sure the selected neighbor points really belong to the same surface or fold, like points along a roof edge.
And the trees, the really messy bits.
For the high omnivariance regions, yeah, like vegetation, they use a simplicial complex-based method. It sounds complicated, but it's good at clustering points that are truly similar, even if they're a bit spread out. It also helps sort of naturally reduce the impact of outliers.
So by picking neighbors much more intelligently within each region type.
They can calculate much more accurate geometric features for each point. Things like eigenvalue-based features, omnivariance, and curvature we mentioned, and also elevation features. These refined features then get fed into a machine learning classifier. In this case, they use random forest to actually label each point: building, tree, ground, etc.
And the payoff. How well did this adaptive approach actually work?
The results were pretty strong. They reported over 91% overall accuracy and an 82% F1 score, which balances precision and recall. And crucially, this was on both high-density data, like the Toronto 3D dataset, and lower-density data, like Vaihingen in Germany. It outperformed other leading methods.
This sounds impressive. Any catches?
Well, they did acknowledge a minor limitation. Some specific classes, things that are naturally very thin or sparse in the data, like power lines or maybe small individual shrubs, were still a bit challenging to classify perfectly. Room for future work there, definitely.
Okay, bringing it back to the listener, why should you listening at home care about selecting point cloud neighbors more accurately?
Yeah, it sounds technical, but the impact is potentially huge.
Right. It means much, much better 3D models of our cities. Think about it. City planners get vastly more accurate data to work with.
Autonomous vehicles get a much clearer picture of their surroundings. Distinguishing a wall from a bush reliably is pretty important.
Definitely. And for disaster management, imagine assessing earthquake or flood damage with pinpoint accuracy using these detailed 3D models.
It really boils down to this. Getting those fundamental relationships right within the data, like choosing the right neighbors, unlocks huge potential.
Sure.
It helps us make sense of increasingly complex information.
Absolutely. This deep dive really shows that figuring out that neighborhood selection was a major hurdle, and this adaptive technique seems to be a really effective solution for urban environments.
It's a great example of how focusing on the details of data structure can lead to significant leaps forward.
So here's something for you to think about. As our digital maps become almost perfect 3D replicas of our cities, how might that change your daily life in the next, say, 10 years?